Hello and welcome back to Math with the Holy Chicken. After releasing my last video, I became aware that many people disagreed with my opinion that pi equals 2. A lot of people specifically thought that pi equals 0. Now to fix this, I'm going to prove that pi does not equal 0. This is an extremely difficult and very long proof, and is going to take me multiple videos to complete. In this first video, I'm going to prove a basic result that we will need in the next few videos. Today, I want to prove that anything times 0 equals 0. Be sure to watch to the end to figure out what the hell this is. Alright, to prove this fact, we need to first recall the definition of 0. There are many definitions of 0. For example, 0 can be defined as the empty set in the definition of the ordinals. Now this is very confusing, so our definition of 0 will be extremely simple. To begin defining 0, first recall that given a category C with finite products, a group object in C is a tuple C mu A to I, where C is an object, mu is a morphism from C cross C to C, A is a morphism from T to C with T terminal in C, and I is a morphism from C to C, such that these diagrams commute, where the product of two morphisms is implicitly understood to be the image under the product bifunctor, except in the case C to C cross C, where it is implicitly understood to be the relevant universal morphism, and alpha, lambda, rho are the associator, left uniter, and right uniter for products, respectively. At this point, I should remark that I was very sloppy in some parts of this proof with which products and morphisms were from the bifunctor and which were induced by a universal property. And there's a big difference, and so you will need to pre-compose at a lot of times with a diagonal morphism in order to make the proof actually work, since I claimed it was induced by the bifunctor in many cases where it was not. I leave it as an exercise to the reader to find all of the places where you need to pre-compose by a diagonal morphism and to make it work. A morphism of group objects phi from C mu A to I to D nu zeta j is then defined to be a morphism phi from C to D in C, such that this diagram commutes. It's easily shown using the commutivity of the above diagrams and the definition of the left and right unitors that phi composed with eta is equal to zeta composed with phi, and phi composed with I is equal to j composed with phi. Note that set is a Cartesian monoidal category. We thus define the category group as the category of group objects in the category set, with morphisms given by morphisms of group objects in the category set. We call objects in group groups. It's easily shown that group also has finite products, so we define the category AB to be the category of group objects in group, with morphisms given by morphisms of group objects in group. Moreover, we call objects in AB abelian groups. Moreover, abelian groups must have their morphisms eta, mu, and I equal to the functions in set that create the group objects in group. So note that the morphisms of abelian groups are simply functions satisfying commutivity conditions, and moreover the images of these functions under the product bifunctors in the categories set, group, and AB coincide, so there will rarely be a reason to distinguish between in which category we are considering the morphisms to be. Let A, mu A, eta A, and IA be an abelian group, or simply A for simplicity. We want to show that the endomorphism set of AB of A is an abelian group. Note that endAB of A is a set, so we first show it as a group. Denote by star the singleton, which is terminal in set. Define eta from star to endAB of A be the star map to 1A, which indeed exists since AB is a category. Define mu from endAB of A cross endAB of A to endAB of A to be the function mu of phi cross psi equals mu A comp phi cross psi. Finally, define I from endAB of A to endAB of A to be the map phi map to IA composed with phi. I leave it as an exercise to the listener to show that these definitions define a group object in the category set. To complete the proof, it suffices to show that these are morphisms of groups, which is easily shown. It is also important to note here that when viewing the singleton as a group object, in which case it forms a group object in exactly one way since it is terminal, we will denote it by bold 0. Note that for any A, mu A to I in AB, and for each n and z, there's an endomorphism alpha n from A to A given by alpha n equals this product of mu composed with this product of 1A, where these products are not the same product, but one of them is a bifunctor and one of them is a universal property that is not the bifunctor. It's slightly different. There's an invisible composition with a diagonal morphism, and I'm not actually convinced that I wrote both of these products the same way. Luckily, these products aren't important, so I don't care enough to fix this. Now, assuming that I've written it correctly, which I probably haven't, it's easily shown that for any morphism of abelian group psi from A to B, there's an equality alpha n composed with psi equals psi composed with alpha n. For this reason, we call morphisms of abelian groups z-linear. Since abelian groups have an underlying group object and group objects have underlying sets, we can define an element of an abelian group A as a function star to A. Let A be C and A be. We call a function phi from A cross B to C Z bilinear if for all f in Hom's set of star A and all g in Hom's set of star B, the compositions phi composed with f cross 1b and phi composed with 1a cross g are Z linear. Define the tensor product A tensor B of two abelian groups AB and AB to be the group together with a Z bilinear map tensor from A cross B to A tensor B, such that for all Z bilinear maps phi from A cross B to C, there exists a unique Z linear map phi bar from A tensor B to C, making this diagram commute. Note that for any pair of morphisms of abelian groups F from A to C and G from B to D, my bad, the composition tensor composed with F cross G from A cross B to C cross D is bilinear. Define the tensor product F tensor G of the morphisms F and G to be the unique induced morphism A tensor B to C tensor D by universality of tensor. Under these definitions, tensor clearly defines a bifunctor tensor from AB to A cross AB to AB. Additionally, it is very easily shown that there exists a natural isomorphism alpha from tensor composed with 1AB cross tensor to tensor composed with tensor cross 1AB, and moreover, it is also very easily shown that with the obvious abelian group structure on Z, there exist natural isomorphisms lambda from Z tensor blank to 1AB and rho from blank tensor Z to 1AB. Finally, it is trivially shown that for all A, B, C, and D and AB, these coherence conditions are satisfied, that is, these diagrams commute. Therefore, AB tensor Z alpha lambda rho is a monoidal category. This fact allows us to define AB enriched category. An AB enriched category is often called a pre-additive category, and they are to rings as groupoids are to groups. For that reason, I've decided to call them ringoids, because I can. Define a ring as a ringoid R, where the objects of R is a singleton. Let ring be the category of rings where morphisms R to S are given by AB enriched functors F from R to S. Hold on, I want to drink my, I have a Starbucks pink drink. Very good. Okay, let's continue. We are now prepared to define 0. Let R be a ring, and recall that since R is AB enriched, if star in R is a single object in R, then end R of star is an abelian group. Let end R of star be the abelian group A mu A to I, where we are without loss of generality taking the morphisms that make it an abelian group to be the same as the ones that make it a group, since they have to be the same by some theorem that some guy proved. For mu from A cross A to A, eta from 0 bold to A, and I from A to A, the morphisms of groups defining A as a group object and group. Arrows in R are given by morphisms of abelian groups Z to end AB of star equals A, so Hom AB ZA is the set of all morphisms in R. This abelian group is isomorphic to A, so we define an element of R to be an element of A, which is previously defined to be any function F from star to A for star the singleton once again. Without loss of generality, we write X in R to denote that X is an element of R. We now define 0 to be the morphism eta. We are now prepared to complete the proof. With notation as before, it suffices to show that 0x equals 0 for some element x of R. However, this requires a definition of multiplication. Recall that multiplication of rings is given by morphism composition comp sub R from A tensor A to A, which is a morphism of abelian groups. Let x in R, and we thus have that x is a function from star to A. Similarly, eta equals 0 is a function from star to A. We thus have that 0x is defined as the comp sub R comp tensor comp eta cross x. Note that since A is a group object in group, we have that mu comp 1A cross eta equals rho A, and we also know that rho A comp f cross g equals f for any functions fg with the same codomains. We thus have that mu composed with eta cross eta equals mu comp 1A cross eta comp eta cross 1A equals rho A comp eta cross 1A equals eta. Therefore, we have that comp R comp tensor comp eta cross x equals comp R comp tensor comp mu comp eta cross x. By bilinearity of tensor, we have comp R comp tensor comp mu comp eta cross x equals comp R comp mu comp tensor comp eta cross x cross comp tensor comp eta cross x. Oh my god. I have 2 more pages of this, Jesus Christ. Since comp R is a morphism of abelian groups, we have that comp R comp mu equals mu comp R cross comp R by commutativity of this is stupid. By commutativity of one of the previous diagrams, and thus we have comp R comp mu comp tensor comp eta cross x cross tensor comp eta cross x equals mu comp r cross comp r comp tensor comp eta cross x cross tensor comp eta cross x equals mu comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x, where the last step follows by functoriality of product. We thus have an equality comp r comp tensor comp eta cross x equals mu comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x. And by bifunctoriality of product, it follows that producting on the left yields the equality I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x equals I comp r comp tensor comp eta cross x cross mu comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x. Composing on the left with mu, I'm not reading. Composing on the left with mu gives this. Since alpha is a natural isomorphism, cross comp one set cross isomorphic to cross comp cross one set, by reversing the arrow in one of the commutative diagrams above, we have mu comp I comp r comp tensor comp eta cross x cross mu comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x equals mu comp I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x. Hold on, I'm drinking more of my Starbucks. Good Starbucks. Okay, note that mu comp I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x equals mu comp I cross 1a comp 1a cross 1a comp r comp tensor comp eta cross x, where 1a cross 1a is the diagonal morphism, and again, there's still diagonal morphisms on the end. You have to keep that in mind. By commutativity of one of the above diagrams, mu comp I cross 1a comp 1a cross 1a equals eta comp f, where f from eta star is the unique morphism to the terminal object. We thus have mu comp I cross 1a comp 1a cross 1a comp r comp tensor comp eta cross x equals eta comp f comp r comp tensor comp eta cross x. Since star is terminal and the composition f comp r comp tensor comp eta cross x is a function from star to star, this must be equivalent to the unique morphism 1 star, and thus eta comp f comp r comp tensor comp eta cross x equals eta comp 1 star equals eta. Plugging in gives us mu comp I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x equals mu comp eta cross comp r comp tensor comp eta cross x. We thus have, by properties of lambda a and commutativity of one of the previous diagrams, that mu comp eta cross comp r comp tensor comp eta cross x equals comp r comp tensor comp eta cross x. Note that this is, once again, our definition of 0 times x. Now recall the other side of the equation, which was mu comp I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x. This is equivalent to the composition mu comp I comp r comp tensor comp eta cross x cross comp r comp tensor comp eta cross x equals mu comp I cross 1a comp r comp tensor comp eta cross x, where we've done away with the diagonal morphism because at this point I've now realized that there need to be these invisible morphisms at the end, so I've just stopped writing it. So by commutativity in one of the previous diagrams, we have that equals eta comp f comp r comp tensor comp eta cross x, where f from eta star once again, since star is terminal, the composition f comp r comp tensor comp eta cross x from star to star must be equal to 1 star, and thus we have the eta comp f comp r comp tensor comp eta cross x equals eta comp 1 star equals eta. Putting the equation back together, we have eta equals comp r comp tensor comp eta cross x. Therefore, 0x equals 0. Thank you for coming to Math with the Holy Chicken. This is our first video out of, I think, 3, where I will be proving that pi does not equal 0. I'm not sure what I will do for the next video yet, but tune in next week to figure out how I decide to do it. Bye.